So, you've probably scrolled through car forums and seen those wild claims, right? People swearing up and down that electric vehicle brake pads literally never wear out, or that driving down a steep hill will practically recharge your battery back to 100%. It sounds like absolute magic, almost like perpetual motion. Well, today we're going to push past the internet hype and uncover the actual engineering truth behind one of the most talked about features of modern driving. Welcome to The Explainer. Today, we're digging deep into the data to demystify regenerative braking. We're tossing the rumors out the window and looking at hard, objective numbers from engineering studies to completely separate fact from fiction. No guesses, just the fascinating science of how this tech really works, how much energy it genuinely saves, and what it actually means for you on your daily commute. Okay, let's take a quick look at a roadmap. We are going to hit 1. Mechanics, 2. The energy reality, 3. The lifespan boost, 4. Slashing pollution, 5. Physical limits, and finally, 6. Maximizing brakes. Let's dive right in.
Section 1. Mechanics. To truly understand the benefits and the limits, we need to know what's happening under the hood the split second you take your foot off the accelerator. In a standard gas car, slowing down is just mechanical. But in an EV, regenerative braking means the traction motor literally runs in reverse. Instead of just slowing the wheels down, it acts as a generator to capture all that kinetic energy. And the real secret sauce here? Brake blending. Your car's electronic control unit acts like a master conductor, making split-second decisions to seamlessly blend the motor's braking force with traditional friction brakes when you need extra stopping power. It's so incredibly smooth, you barely even notice it happening.
And it's just a brilliant shift in automotive engineering. Think about the traditional internal combustion method. You press the pedal, friction pads clamp down, and all your forward momentum is completely wasted as heat, just radiating away into the air. But the EV method totally flips the script. It takes that exact same kinetic energy and recycles it into electrical current, routing it right back into your battery. It's literally the ultimate form of vehicular recycling.
Section 2. The energy reality.
Now, let's tackle the most exaggerated claim out there and get a reality check on how much energy is actually recovered. There is a massive contrast between expectation and reality here. A 2024 engineering review found that in everyday, real-world city driving, EVs typically recover between 25 and 40% of the energy used for braking. Why so low? Well, most city braking happens at very low speeds where the system is just inherently less efficient. Now, under highly favorable conditions, component manufacturers say production systems can hit up to 70%, and that absolute peak, 92.5%. But that's only achieved in experimental lab settings using supercapacitors. That is a huge difference from what you're getting on your morning grocery run.
Because of those fluctuating variables, we've got to talk about range gain. It's honestly impossible to pin down a single universal percentage that applies to every car. Recovered energy isn't perfectly converted into forward motion. Actually, scratch that. It's more like the energy still has to survive charging and discharging losses within the battery system before it ever moved the vehicle. Plus, your driving environment is a massive factor. If you're battling stop-and-go city traffic, you're going to see a wildly higher regenerative benefit than someone just cruising at a constant speed on an empty highway. All right, Section 3, the lifespan boost. Even if you aren't getting infinite range, your physical hardware is getting a huge upgrade. A typical gas car burns through its brake pads every 30,000 to 60,000 miles. It's an annoying, regular maintenance headache. But with EVs, because the electric motor handles the vast majority of your everyday deceleration, those physical friction pads are barely even touched. As a result, EV drivers are seeing their brake pads last anywhere from 80,000 to 150,000 miles. That's roughly 2 to 4 times longer. For some drivers, the brake pads will literally outlast the car itself. You might never have to pay for a brake job again.
However, there's always a catch, right? It's very much a use it or lose it situation. Because you're relying so heavily on the electric motor, your physical friction rotors are just sitting there, basically rusting from boredom. In humid environments, or places where they salt the roads in winter, this underuse makes them super vulnerable to surface rust and corrosion, so you might actually end up replacing those heavy metal rotors due to rust way before the pads themselves ever wear out.
Section 4, slashing pollution. Let's talk about the unsung environmental hero of this tech, going way beyond just tailpipe emissions. 83%. That is a staggering number. Brake dust from physical pads grinding against metal rotors is a very real, very measurable source of particulate pollution in our cities. But a 2025 EIT urban mobility study covering London, Milan, and Barcelona found that battery electric vehicles cut urban brake dust emissions by a massive 83% compared to traditional gas cars.
And it's not just one isolated study either. Multiple peer-reviewed sources back this up. A UK study measured EV brake particulate output at roughly a third to a half of internal combustion levels. Another 2023 simulation study put the potential reduction anywhere between 64 and 95%. So what does this actually mean for you? It means significantly cleaner air in your neighborhood. And it unequivocally proves that the pollution-slashing benefits of regen far, far outweigh any extra tire wear caused by the heavier battery weight of an EV.
Section 5. Physical limits.
To give you the full engineering picture, we have to talk about the boundaries. There are two extremely common scenarios where regenerative braking genuinely loses its power, and it all comes down to battery chemistry. First up, cold batteries. When lithium-ion cells get cold, their internal resistance spikes. They literally cannot safely accept large charging currents, so the car's computer automatically dials back the regen. Second, near-full batteries. If you're sitting at 100% charge, there's physically nowhere for that generated electricity to go. This is exactly why you might pull out of your driveway on a freezing morning or right after a full overnight charge and suddenly feel like your car isn't slowing down like it normally does. It's not broken, it's just protecting itself.
Finally, Section 6, maximizing brakes. So, how do we use all this data to get the absolute most out of our cars? Here is a quick, actionable checklist. Step 1. Leverage one-pedal driving or strong regen modes if your car has them. You only get the benefits if you actually use the hardware. Step 2. Precondition your battery. Warm it up while the car is still plugged in on cold mornings so your regen is fully active the second you leave. Step 3. Manage your highway expectations. Regen is amazing in stop-and-go traffic, but it's not going to do much for you on a long, flat interstate cruise. And Step 4. Always keep up with your mechanical inspections. Just because the pads aren't wearing down doesn't mean you can ignore brake fluid or the risk of rotor rust. We've seen how today's systems brilliantly recycle energy, dramatically extend hardware life, and clean up our city air. But as the tech evolves at lightning speed, here is the big question we're facing now. If we're already recovering 25 to 40% of our braking energy in real-world city driving today, how quickly will those experimental supercapacitor-driven lab systems become the new standard? Will the cars of tomorrow routinely capture 90% or more of our stopping power? It's an absolutely thrilling engineering frontier, and I, for one, cannot wait to see where it takes us next. Thanks so much for joining me for this explainer, and keep asking the right questions.